Fabrication of monolithic transistors. Fabrication steps for integrated NPN transistor. A single crystal of P-type silicon wafer is taken. Buried N plus layer is diffused. The dopant in this case is arsenic. All oxide is etched and N-type epitaxial layer is grown on the entire surface. The process of P plus isolation diffusion is performed to produce isolated N-type islands surrounded by P region. After isolation diffusion, P-type base is diffused. Here two steps are involved: pre-deposition and drive-in cycle. The second step is controlled to get a PN junction about 3 microns below the surface. N-type emitter diffusion process is performed into the base so that the base width is 0.7 micron. The holes are etched in oxide mask to prepare the wafer to accept electrical connections. Wafer is placed in vacuum and heated, and aluminum vapors are allowed to alloy with the silicon and oxide. Aluminum layer 1 micron thick is vapor deposited. Aluminum is selectively removed by photo etching, leaving only interconnections and bonding pads. Diamond stylus is scribed across the wafer and chips are separated. Chip is bonded to final enclosure and fine wires bonded to aluminum pads. These wires connect the chip to pins of the can or enclosure. Final configuration of the integrated NPN transistor is shown in figure. Lateral PNP transistor. This uses the standard diffusion techniques which has been used for the NPN transistor. The lost in diffusion is eliminated. While the P base for the transistor is made, the two adjacent P regions are diffused for the emitter and collector of PNP transistor. Here, current flows laterally from emitter to collector. So this shows the fabrication of monolithic diodes. First we have layer on wafer on a N-type silicon substrate. We have the SiO2 layer is made. Next we have masking lithography, a photoresist and a hole is made through etching, and through the hole ions are diffused, ion diffusion, that is nothing but selective area doping, and finally metal contacts are established to create a diode. Fabrication of FET junction field effect transistor. The epitaxial layer of the monolithic IC forms the N channel of the JFET. The P plus gate structure is formed in the N channel by diffusion process or ion implementation procedure. The drain and source connections are made through the ohmic contact regions. The ohmic regions are diffusion regions with N plus regions of higher doping concentration. They provide good ohmic contacts. Next we have metal oxide semiconductor field effect transistor or MOSFET. The sectional view of an N-channel enhancement MOSFET is shown in figure. The substrate forms the channel of the MOS transistor. The metallic or polycrystalline silicon gate G is thrown over an insulating SiO2 layer. This is formed by oxidation process. Normally, aluminum is used as the gate electrode material. The polycrystalline silicon or polysilicon doped with the phosphorus is conductive, and it replaces the aluminum gate in recent monolithic fabrication processes. Next we have CMOS complementary MOSFET. The NMOS and PMOS enhancement devices can be fabricated on the same silicon chip. These devices are complementary MOSFETs and are abbreviated as CMOS. The four important CMOS process technologies are N-well process, P-well process, twin-tap process, and silicon on insulator SY process. CMOS inverter circuit and its cross-sectional view of CMOS IC is shown. In the N-well process, an N-type well or tub is diffused in the P-type substrate. The PMOS transistor M2 is fabricated within this well. The N-well region acts as a substrate for the PMOS transistor. The additional processing steps are the formation of N region and the ion implantation step of P-type source and drain regions. The P-well process are the commonly used forms of CMOS fabrication, and the process steps are similar to N-well process, except that the P-well diffusions are formed for fabricating NMOS devices. The twin-tub CMOS process employs both the N-well and P-well diffusion regions for fabricating PMOS and NMOS devices respectively in the wells. The emerging process of SY technology achieves closer packing of PMOS and NMOS transistors, and it avoids such problems as latch-up and lower parasitic capacitances. In this process, a thin layer of single crystal silicon is epitaxially grown over an insulator such as sapphire or magnesium aluminate spinel. Next we have fabrication of monolithic integrated resistors. The basic technique for obtaining a resistor in integrated circuit is by utilizing the bulk resistance of a defined volume of semiconductor region. Four different methods are available for fabricating integrated resistors, namely diffused resistor, epitaxial resistor, pinched resistor, thin film resistor. Diffused resistor, in this method, a resistor is formed in one of the isolated regions of epitaxial layer during base or emitter diffusion. This type of resistor is very economical. Limitation is the small range of resistances. The value of the resistance depends upon the surface geometry, that is length, width and width and upon the diffused impurity profile. So sheet resistance, we have the base resistor, C represents the emitter resistor, and the last top view showing dimensions for a 4000 ohm diffused resistor. Epitaxial resistor, large value of resistance than possible by base or emitter resistor can be achieved by using an epitaxial collector region as shown in figure. So this is epitaxial resistor. pinched resistor, the pinched resistor sheet resistivity of a semiconductor region can be increased by reducing its effective cross-sectional area. A pinched base diffusion resistor is shown in figure. Next we have thin film resistor. In this, a very thin metallic film, usually of nichrome, of thickness less than 1 micrometer, is vapor deposited on the SiO2 layer. Using masked etching, desired geometry of this thin film is achieved to obtain suitable values of resistors. So this diagram shows cross section of a thin film resistor. Next we have fabrication of monolithic integrated capacitors. P and N regions forming the capacitor plates. The dielectric of the capacitor is the depletion region between them. So this is called a junction type IC capacitor. Next we have MOS capacitor. A commonly used capacitor is the metal oxide semiconductor capacitor, for which the cross-sectional view is shown in figure. It is basically a parallel plate capacitor with SiO2 as the dielectric. The heavily doped N plus region formed during the emitter diffusion forms the lower plate, and the thin film of aluminum metallization forms the upper plate of the capacitor with the SiO2 as the dielectric. Thank you. Fabrication of monolithic transistors. Fabrication steps for integrated NPN transistor. A single crystal of P-type silicon wafer is taken. Buried N plus layer is diffused. The dopant in this case is arsenic. All oxide is etched, and N-type epitaxial layer is grown on the entire surface. The process of P plus isolation diffusion is performed